Welcome to my new calculus channel. I am John Gabriel. In this video I'm going to be talking about the new calculus and describing it or teaching it in a way that people who are not very mathematically inclined can understand. This is probably very useful for professors of mathematics because they are the most ignorant and need the most help. So if you're a mathematics educator or a professor, you need to be paying attention. Okay, so let's begin with the very basic definition. What is a point? Well, very simply this: a point is just an idea. It's the concept of location or place. And it happens to be the foundation of all geometric objects. All other geometric objects are obtained from the point. So for example, to arrive at a line we need 2 points, right? 2 points are the symptom of a line. Symptom of a line or a path. What does symptom mean? It's a Greek word. It means sign, okay? A sign. 2 points is a sign. And what's special about these 2 points? For example, we can have infinitely many paths between these 2 points, yes? Maybe I should make these 2 points a little bigger. Let's just draw circles there. Okay, there's one circle. So, boom, boom. Okay, and let's copy that. Copy, paste. All right, let's put them over there. There we go. All right. So now, that there is a path between the 2 points. There are infinitely many paths between the 2 points. And what's special about all those innumerably many paths? Well, there happens to be one that is the shortest path between the 2 points. Okay, that's supposed to be a straight line there. Let me just do this. That's not strictly speaking a straight line either, but I think you get the idea. And so that short line, that green line, is the shortest distance between these 2 points. So 2 blue points are the symptom of a path. How about 3 points? 1, 2, 3 different points, okay? What are they the symptom of? Well, once again, we can have infinitely many paths between these 3 points, can't we? Yeah? And there'd be nothing special about any of those paths unless they're different, unless that particular path is different from all the others. Well, it turns out that if we take the shortest distance between the 3 points, we arrive at a triangle, right? So a triangle is the symptom of 3 points of the triangle. 3 points are the symptom of a triangle. Yes? Okay. I must be getting Alzheimer's. Just kidding. All right. So similarly, 4 points, the system of a rectangle, or the symptom of a rectangle, and so on. So let's get back to this new calculus for dummies. A geometric object consists of 1 or more points. Definition: a path describes a distance between any 2 points. As you see in that diagram there. All the lines, and they don't have to be straight, in the above diagram are visualizations of paths between the 2 points. Here's a path, and here's another path, and so on. And as you've just seen, there are innumerably many paths. A path is said to be continuous if no portion is disjoint from any other portion also on the path. So this gives you an example of discontinuous paths, because there are disjoint paths. Yes? So let's continue. A straight line is a geometric object which describes the shortest distance of path between any 2 points. It's very important to note that the only geometric object that possesses the attribute of slope, gradient, or inclination is the straight line. Okay, no other geometric object possesses that attribute. While some might say the gradient of the curve at a point, what they really mean is the slope of the tangent line at that point, because a curve, which is not a straight line, does not have a slope. So the next definition in the new Calculus for Dummies is a straight line is said to be a tangent line to another geometric object such as a curve if and only if a portion of the straight line, this straight line here, intersects the curve in exactly one point and does not cross the curve anywhere. It also has to extend to both sides of the curve. Okay, it's a finite line. A tangent line is a finite line. If it crosses the curve in any other place, then it's not tangent at any other place. It's only tangent at this point here if it meets those three conditions. In other words, what are the conditions? Well, one, let's write this down. One, it intersects in one point. Two, extends to both sides of point. And three, crosses the curve nowhere. Okay, this is very important because if we have the cubic like this, in mainstream calculus it's falsely believed that there is a tangent line there. There isn't a tangent line there. There are actually half tangents, but there is no tangent line there because a tangent line may not cross the curve. Okay, tangent line may not cross the curve. And that is the original definition which Newton understood, which, by the way, if Newton's understanding was wrong, the root approximation theorem or method that he came up with wouldn't work. And I'm not going to go into that right now, but I'll probably leave that for another video. So let's get back to this document. A path is said to be smooth if and only if one tangent line with a defined gradient can be constructed at every point in the path. So a path is still considered smooth if there are points of inflection. First of all, here on the left is a smooth path, okay, because we can only construct one tangent at every one of the points. But in this non-smooth path here, we can construct as many tangents as we like at this point here. Do you see that, where the cross is? So this path here is not smooth because we're only allowed to be able to construct one tangent. If you can construct more than one, the path is not smooth. And an example that you see typically in mainstream math, which is almost sickening because it appears in just about every paper, shows what idiots modern educators are, is the absolute value function, where they talk about this point here not being differentiable. Well, of course it's not, because you can construct infinitely many tangents at x is equal to 0. Okay, so this here is the graph of the absolute value of x. This is the graph of the absolute value of x. Okay. So now, excuse me, what is a point of inflection? Well, we just saw an example of the cubic right now, where you have half tangents. So, in other words, a point of inflection is one where the curve doesn't actually have a derivative in the new calculus, okay? And that's the correct treatment of an inflection point. So if we just look at this characteristic or attribute of slope, every straight line in a plane has two important characteristics. It describes the shortest path or distance between 2 points, and it has an angle of inclination or a slope which is measurable from the horizontal line. And most of you with a high school education should know this stuff. And here we have more description of the angle of inclination. You can see this document. You can just type New Calculus for Dummies on the web and you'll be able to get access to this document. So let's go to the tangent gradient or the slope problem. So if you have a slope like this, a curve like this, and you want to know the slope of that tangent line, then the best way to approach it would be the way that the new calculus approaches it, which is by constructing a parallel secant line. Now some will say, well, you know, how do you do that? Well, there's really nothing to it. It's a geometric axiom. Okay, so if you have any curve like that, or even just a curve like that, it is always possible to construct, let's say, well, let's do this. Let's say that this here is a tangent line. Come on. Oh boy. Somehow I'm not able to do that with my pen. I am. Okay. So let's say we have a tangent line here. And now we construct parallel secant lines like that. Okay, so now we're always able to construct parallel secant lines. It doesn't really matter what the curve is. Okay? Oops. I didn't mean to do that, but it doesn't matter. Let's just make that secant green. Okay, and now come back here again, and let's do the same here. So over here, we can have another tangent there, and then we can construct parallel secants anywhere we like along this curve, right? So anywhere up here, we can construct parallel secant lines. Or there will always be a parallel secant on this interval here. So if you're looking at the x-axis like this, you'd have an interval there, that short interval. So anywhere in this interval or in this interval, you'll be able to construct a parallel secant line to this tangent. This is a geometric axiom. It doesn't need any proof. Okay, so now the new calculus solves the problem of the derivative or differentiation by finding the slope of a secant line that is parallel to the tangent line. Right? So let's see what that means. On first inspection, this is almost an impossible task. It took 330 years to find a rigorous method, actually longer. In the new calculus, this is possible because of the secant theorem. And the secant theorem is what I described to you inside here. And I'm not going to go into it in great detail because I've written articles in it and you can read those up for yourself. Before we study the secant theorem, let's take a look at some basic theory of gradients. So we already discussed some of these things. And let's look at this particular diagram here because it's very important. The slope of this line here is just simply the difference in the vertical distance over the difference in the horizontal distance. So if f is a planar function and this is the point of one of the secant, this is one of the endpoints of a secant, and this is the other endpoint of a secant, then the gradient k of this line, whatever it is, k can be anything, is given by this formula here. Yes, where c minus m is less than c is less than c plus n. And to see how that works, we look at this diagram here. Okay, I've drawn it in the opposite sense, but it doesn't really make a difference. This distance here over this distance here is equal to the slope of the secant, and hence the slope of the tangent line at a certain point c in this interval here. Okay, so c is somewhere in this interval, and k is the gradient, and as you can see, k times m plus n is the length of that line. Just simple analytical geometry. There's nothing to it. Grade 8 mathematics. And so, as we go through a document, you can see that m plus n will divide all the terms of the numerator. There's a simple proof of this. I do go into a bit of detail here, but it's easy to prove. You just take a straight line and calculate k, and you'll see that if you do it with generic terms and symbols, you will arrive at the fact that neither m nor n are necessary in the calculation of the slope or the gradient. There is a more involved proof of this, something called divisibility identities. I'll put a link to that on my website, and also a general proof of it using the Gabriel polynomial. But then you'd have to learn what is the Gabriel polynomial, and that requires that you already know what Taylor's polynomial is. So this here is perhaps the simplest method, or the simplest proof, that every straight line, every parallel secant line will have this gradient, as you see in formula G here, and thus it will be the slope of the tangent line at C. And all these things are proved in my articles. Okay, so the secant theorem, just very briefly, in this Calculus for Dummies, says that there are infinitely many secant pairs in here that satisfy the slope of the secant lines, which are parallel to C. There is a special relationship for every continuous and smooth curve in calculus between this distance here, m, this distance, n, and C. Okay, and that relationship is given in the auxiliary equation, which I'll talk about in another YouTube video and exactly what it means. But the auxiliary equation takes three parameters, C, M, and N. Okay, I've left out C here because it wasn't really necessary in this case for the purposes of the demonstration. But every one of these secant lines has a unique pair which will satisfy this equation. Okay, and m plus n is never 0 because no secant line meets the tangent line exactly at the point C. Otherwise it's not a secant, right? It will just degenerate into a point. So no secant line can have m plus n equal to 0. Only the tangent line. And there is no use of limits in the new calculus, because even after this quotient has been simplified, m plus n cancels out with every term in the numerator, because it is a factor of every term in the numerator, and we're left with a term without any m or n that gives us the slope. Okay, so and it makes sense because at the point C, m and n must be 0, because m and n are the distances from the point C to the endpoints of a secant. This document will be uploaded and you'll be able to take a look at it. So we can derive the formula of the derivative as follows. It's equal to k plus q mn. Notice that this term here is always 0. And this is in fact what is called the sum of all the remaining terms, and it is the auxiliary equation. A very powerful feature of the new calculus, not possible using Newton's flawed calculus. So I repeat that. The auxiliary equation is only possible in the resilient and rigorous new calculus formulation. It's not possible in new calculus, in Newton's formulation. And so here's another here are some examples of how to find the gradient using the new calculus. Yes, pretty simple. And we see here that Q00 is equal to 0. That's a simplified gradient. And there are some examples in here that you can look at. And so you can even look at one for the cubic. These are simple examples, but there are examples in my other articles which deal with cubics and quartics and sine and cosine, hyperbolic functions. In fact, all the conics. There is not a single function that can't be differentiated with the new calculus. And even proving the differentiation rules is significantly simpler than the flawed calculus, because it contains no infinitesimals or infinity or limits. Everything is very straightforward. The proofs are easy. The chain rule is easy. Just a little comment here. Franklin Cottrell, some guy wrote a dissertation on the chain rule, and I think it's over 200 pages long. That's kind of funny, but just goes to show you how ignorant mainstream academics are. And here I give a special case of the chain rule using the new calculus. Okay, so this is a little more than what was intended for this document, but it's right at the end and not necessary if you're just getting used to an introduction to the new calculus or to calculus itself. So you can take a look at this new calculus for dummies and learn how the new calculus works. Now, in this document I've only described differentiation. However, the new calculus integral is also defined without limits and without infinity or infinitesimals. So you can read my articles at the new calculus site, and in particular look at the proof of the mean value theorem, which is proved both using the flawed calculus and the new calculus, so that you can get an idea of how rigorous and how improved the new calculus is over the flawed calculus or the mainstream calculus. And so I hope you've enjoyed this YouTube video on the new calculus for dummies. This is the new calculus channel. I'm John Gabriel, and I hope you'll join me again soon for another presentation on the new calculus with a lot more topics, and I'll also be discussing other hot topics that are not part of the new calculus. Thanks for joining me.